So let's quickly talk about bicycles. Well, actually what I want to talk about is a flexible drive mechanism like a chain or a belt. So a chain needs to always be in tension so that it is nicely wrapped around the sprockets of the bicycle. Okay, so on a bicycle, this mechanism at the back there is called the derailleur or something like that. That's the spelling over there. And it's basically got a spring mechanism in to always make sure this chain is under tension. Okay, so the reason for the tension is if there wasn't tension, it will wobble around and then start jumping teeth. Now, a belt, which is a similar concept to a chain, has also got the requirement that there has to be tension in a belt, especially in a flat belt which doesn't have teeth like the chain does. Then the friction of the belt over the pulley is actually what causes it to transmit the driving power. Okay, so I just have another example over here. This is an example of an engine which has a timing belt. So this belt does actually have teeth similar to a chain. And on the left hand side there, it's got a little bearing. So that bearing is used to apply a force on the belt to make sure that the belt is always in tension. Obviously, if this belt wobbles around, it will go out of timing, and then the engine's pistons will actually hit the valves, and the engine won't function as it's supposed to. In this one's case, it's got actually 3 bearings. The one happens to be the water pump, the other one is just a little roller, and this one over there is a belt tensioner. So basically what we're doing is the belt has a fixed length. It doesn't become longer or shorter in its life. So what we do is if we apply a force on the belt and we deflect the belt, then we can deflect it up to a point where the belt is tightly pulled around all of the pulleys, if you want to call it that. Okay, so this tensioner actually needs to be able to move, to be able to pull the belt tightly. There's just a picture of an engine similar to the one in the previous picture, and over there we've got the tensioner. So let me quickly show you what I'm talking about. Okay, so in this one's case, remember the idea is we want to have tension in the belt. So we need something. This one has a bearing inside there. That little ring inside there is a bearing, a journal bearing. So the journal bearing is for rotation purposes. So if we apply a force over there, we're going to rotate the pulley to the right hand side. Okay, and then just want to see what the questions are. Yes, definitely. So this is the tensioner, and there we have a pretty huge timing belt. So we want to pull this belt tightly over all of the pulleys. So what we do is we have this pulley, and if we apply a force here at the left, we can rotate that pulley and basically change the geometry of the path of the belt. And if we move it in the right way, we can actually pull on the belt. And that would make the belt be pulled tightly around all of the other stuff. Okay, so that is just an example of a belt tensioner and a belt. Okay, guess who's going to be doing a timing belt replacement on his car sometime soon. Okay, so that was just an intro so that you can see what the purpose is of a belt tensioner. It is something that can move so that it can pull on a belt while it's moving to make sure that the belt is tightly pulled around all of the things that it's going to be providing driving force to. Okay, that brings us to assembly drawings, lecture number 5. So this was actually the exam of 2010, and it says, the detailed drawings of a number of components are shown in figure 2. The components form part of a belt tensioner. Now we know what a belt tensioner is. There are standard components used in the assembly which are not shown in figure 2. Draw the following views to fully describe the assembly. An external principal view and a section right view. The section is illustrated on the schematic layout of the assembly. The section is through the centers of the tension wheel and arm hinge. Okay, now that we've seen what the tensioner looks like, tension wheel and arm hinge are also things that would kind of make sense now. This is the wheel. So in this one's case, it's actually got a roller bearing on the inside, not a journal bearing. And this is the hinge point. Okay. Interesting stuff. Now the one we're going to do today is obviously a lot simpler than that one that I just showed you. So this is the schematic. Remember now, a schematic drawing is not a memo. It is just a basic idea how the views would be laid out. So please don't assume if a line is behind something here that it must be behind it. This is just a schematic. Okay, but what it does show is more or less the location of components relative to each other. So we've got some other long component over there, a thin one there, a flat one at the bottom, a loopy one there, and a circle one at the top. Okay, let's have a look at the components. If I start at the top right, I've got a long component. It's got a length of 182 plus 40. So that's triple 2 if I'm not mistaken. So it's 182 plus 20 on that side and 20 on that side. It's got a width of 96, thickness of 16. There we have the hole with a diameter of 16. There are 2 slots. There's a slot and there's a slot. Next component. Here we have some tall component with a hole at the top and the bottom and something that goes to the right hand side. It does look vaguely familiar. Okay, at the bottom there, it's got a diameter, a hole with a diameter of 19. At the top, it's got a hole with a diameter of 16. There, it's got a M16 thread, 54 center to center, 14 from that plane to that plane. Yes, you are correct. The width at the top there is 30. It is supported on a vertical pillar or web or rib or whatever you want to call that thing. It's got a thickness of 15. The gap on the left hand side is 4 millimeters. So the gap on the right hand side is 30 minus 15, that's 15, minus 4, so that gap on that side is 11. At the bottom, it's got a hole with a diameter of 19, length 52. Beneath that, we've got a wheel with a width of 76. That shouldn't be diameter. I'll just put my hand in front of it. So width of 76. Inside diameter of 25. Inside length of 54. If the inside is 54, the outside is 76, then the gap on the side is 76 minus 54, that's 22, divided by 2 is 11 this side, 11 that side. Outside diameter is 76 as well. At the bottom there, we've got something with a thread of M16. It's got a length of 47, the threaded part, then it's got a diameter 12 with a length of 9, and it's got a 17 millimeter high head. That head is not hexagonal or six-sided, it is square. So this is a special kind of bolt. Above that, we've got a little shaft. The shaft has a diameter of 19. We've seen that at two places somewhere. There we have a diameter of 19. Where's the other place? Okay, one place so far then. This length is 52.5. This length is 52. So if I put this pin through that component, it's actually a half a millimeter longer. Meaning if I put a nut on that side and I bolt this face to something, if that one is around there, it will be able to still rotate because I'm not clamping it in too much. Okay, diameter 19, diameter 16. The big end has a diameter of 28. Then we have another shaft, also diameter 16 and diameter 19. This one, diameter 19, has a length of 54.5. It's got diameter 4 holes for lubrication. So for lubrication will tell me I'll probably need a grease nipple somewhere. There we have the M6 thread, that's just like where the grease nipple will go. That hole is 9 millimeters from the side. Also diameter 28. Then the last component is this little pipe. That pipe has an inside hole size of 19, outside diameter of 25. It's got a length of 42 plus 12, 54. Okay, that one has a diameter of 19 on the outside, 19 on the inside, 54.5, 54. So if I put this bushing around the shaft, it will be free to move axially by half a millimeter. Okay, outside 25, length of 54. We've seen that somewhere before. Length of 54, inside of 25. So I can put the bushing inside of the wheel. Okay, let's have a look at this bushing. Inside of this bushing, there's a random rectangle, but the dimension for the rectangle says diameter 22. So that is basically a groove that's cut on the inside of this bushing, all around the inside circumference. Okay, so there's a groove in the inside. And there's also a 2 millimeter wide groove in the axial direction. It almost looks like a keyway. Now the question is, what is the purpose of this stuff? Should we put a key in there, or what should we do? Let's look at the location of this. The width of that groove is 6 millimeters. It is 12 millimeters to the left-hand edge, so to the middle of that, it's 12 minus 3, so that's 9 millimeters from there to there. If we put this bushing over the shaft, that 9 and that 9 would line up. So basically the purpose of this block is the grease will come in, go out the holes, fill up that ring inside of the bushing until it finds that little keyway groove. Once it finds the keyway groove, it will transmit the grease in the axial direction as well. So basically the purpose of this groove is the grease will flow into the shaft, out the holes, into the groove until it finds that axial slot, and then it will fill up that slot. So it will allow the grease to be distributed all along the length of the surface of the. As this bushing turns, it will distribute it all around the surface. Yes, exactly. Okay, so let's just double check the length. This one was 54, that's 54.5. This one is 52.5, so if I put the bushing over there, the shaft will clamp down on the bushing. This bushing doesn't have a hole drilled through it like the one in the test, which would hint that the relative rotation is on the outside. So it would make sense to have that half millimeter gap there. So the bushing goes on there, it cannot go on this one. Good. Now let's start to draw. So I'm going to start by drawing the shaft. Well, I should probably start by planning. So this is the view layout. This one on the left, section view on the right. I usually start with the section views because there's where the most marks would lie. So section view here, normal view over here. I think I'm drawing a little bit too small for you guys to be able to see. It's a difficult balance with the thickness of the pen that displays nicely on the camera and allows me to still make enough detail in my drawing. Okay, so there's the shaft. There's the threading. Okay. Into this shaft, I'm going to draw my grease nipple. something like that. Then the diameter over there was 28. The outside of the bushing was 25. The bushing was half a millimeter shorter than this, so you can either draw a quarter of a millimeter gap on each side, or I'm going to rather opt for just drawing the gap on the one side. 28, 25, and then the wheel will be drawn on top of that. These holes had a diameter of 4. That groove had a width of 6, so the groove is slightly wider than the little hole. And I'm going to also draw that little axial groove. You can draw it at the top or the bottom, just to show how the grease will be distributed in the axial direction. Now we can hatch. This is the bushing, so we will cross hatch it. Then let's do the hatching on the shaft as well. Okay. Then that goes into the center of the wheel. Now you'll notice the wheel overhangs by 11 millimeters, so it will not end where the shaft ends, it will go wider than that. I noticed many times in the tests and practicals that people forget these lines in the background. That's an unnecessary mistake. That it costs you 1.5 marks or so for each of those. Well, for the pair, but still. Okay, good. I kind of forgot to mention, we can see here that the wheel goes in from the left-hand side, and that's why I turned the shaft around. You see on that one there, the shaft comes in from the left-hand side, and in the question it was drawn from the right-hand side. So that's why I turned it around. Then let's quickly check this component. Remember we said the gap on that side is 11. And when we calculated this gap on the side of the wheel, it was also 11, which shows me that this wheel physically cannot be inserted from the left of this component. It has to go in from the right because there we have an 11 gap. That side it's only 4. Okay, so it goes in from this side. If we look at this shape is in the correct orientation according to the schematic. So if I put this one in there and I do a right hand view, then it means this view wouldn't be in this orientation, it would be flipped 180 degrees. The diameter at the end there is 30. That is 28. That side of the wheel is 36. So that means and there is a half a millimeter gap as well. Yeah, if you want, we can put a washer in there. Like that. Okay, good. Now it goes down. So what you can do, sometimes if it's hard to get the proportions right in this view, you can start to draw the other view and then update the information from there. So center would be somewhere there. You need to show the threading on the shaft as it was given in the question. So in this question, the shaft had a length of 45 over there. That cylinder had a length of 30. So it means there's 5 millimeters of thread visible on the inside over there. Okay, there's the wheel. Behind the wheel, we've got that bracket coming down. Comes down straight at the left. Straight down at the left and a little bit of an angle at the right. Okay, we can quickly complete this one. There's a circle. Let's start from the inside outward. So the whole of the grease nipple, the head of the grease nipple, the hex of the grease nipple, that edge, the outside edge of the shaft, then the wheel, then those are roundings, so we can't really show it as a solid thick line. So what you can do is you can use a thin line, thin pencil. Is that one and two more somewhere in the middle. Okay, not confusing at all. Good. Now it must come down, and then it's got a circle with the inside of 19. The outside was not given. It was given. That corner lines up straight with that one at the top, so that outside has a diameter of 30. So radius 15. What's interesting to note though is this location where it goes has a radius of 18, so it's smaller than that circle. So the last two circles I drew using my thin erasable pencil was for that inside rounding over there and that rounding over there. So if you left those two out, it's also probably not wrong. Okay, so then it goes down to the bottom, but remember now the bottom had a radius of 18. Slightly bigger than the radius of the bottom of this arm. So generally we aren't super strict on the thick or thin lines. If it is in the right place and it makes sense to be there, you won't be penalized for that. Okay. So this one comes down to somewhere there. Let's check what it looks like. Okay, it's got a little bit of a step going out there. And remember, it is now flipped 180 degrees, so the cylinder is pointing to the left. Okay, now also remember this had a length of 52. The shaft that went through there had a length of 52.5. The diameter over there was 30. That radius was 18, so it will be bigger, meaning this will be bigger. Okay, I think this gap is maybe drawn a little bit too big. I'm just going to make it slightly smaller. That's a bit better. Okay, so the reasoning was that I can get the height for that part and the location for the center and the bottom. So you could do it that way, you could finish the one. It was just to help me with my proportions a little bit. Okay, if we want, we can add a washer. And then add the nut. Finish the threading. Okay, so let's quickly have a look at this base component. So you would notice there's a bit of a radius over there and a straight line. If we look at it on this side, that's the little corner and radius that I drew over there. The same happens on the other side, and I know that because in my top view it has the same double line. Okay, now In this view, remember we're now cutting through the middle here, so everything on the right hand side falls away. So behind this pillar we'll have that little ridge in the background. From the pillar to the center is 14. That ridge has a width of 16. So the ridge will be slightly behind the pillar, similar to what the one in front does. So basically what I'm saying is there is something from the back coming out and then going down. You won't really lose marks for proportions unless it makes other components not line up at all and then physically change the geometry of the components. But proportion wise, there won't really be any marks lost for that. Okay, so now I'm just going to do the hatching for this vertical arm of mine and then for the base. Now I must just be careful that I don't make this pattern over here the same as the wheel or the shaft. So I'm going to use a different angle for this one. Okay, then nut, washer, shaft. There's the shaft. There's the nut. And slightly bigger than the nut, we've got the washer, just because that's the way I do it. Then remember that M16 thread, that's where this square head bolt can go in. The height from the platform to the center of that component is 16. So that means that height, if this L shape is vertical, is 16. The bolt had a open end with a length of 9 and then a threaded length of 47. So that was 16, so just more than half of that length would be the end of the thread. Like that. So now what's happening with this thing is As I rotate this square head thread or bolt, it will screw into this thread and it will progress downwards. But it can only go down up to the point where that point of that bolt makes contact with that surface over there. So once it makes contact with that surface, if I continue screwing in the bolt, it will actually start to lift up. So as the bolt relative to this L shape goes down, it will make contact with the part at the bottom, and as it continues to go down, it will start to lift up that shape or that part over there, which will cause the wheel to move to the left. So I would now typically have a belt around the wheel like that. So as I tighten that bolt, it will move the wheel to the left, which will pull on the belt to make sure that the belt is tight around my pulleys. Center lines are important. You will lose a lot of technical errors unnecessarily if you skip to add the center lines. What prevents the bolt from loosening over time? Nothing. So in this one's case, technically what you could have done, if you were worried about that, you could add a locking nut at the top there. But it wasn't part of the question, so we didn't specifically expect people to know to add a locking nut there. But yes, technically speaking, if you wanted to make sure that it never comes loose, you could have done that. Oh, it definitely screws into the thread, it just isn't tight into the thread. So typically the force on the belt pulling to the right will have a downward force on the bolt, so the bolt will want to pull up on that, and then there will be friction between this component and the bolt. But technically, out of a loosening by itself point of view, this is the best way to do that. Just for interest, that center line over there is the one in the background. Then you add all of your part names, numbers, and all of that. And this is then the memo. You'll notice a partial top view for the mounting dimensions. That wasn't asked. Students who did that by themselves got a bonus 5 marks or something. Can't remember, 3 or 5 marks. Yes, this memo is on ClickUp already. It's just the last slide in Assembly 5.